Now let's talk about the concept that we already observed, but I haven't introduced the proper definition. So suppose that we have an autonomous differential equation, and recall that equilibrium solutions of an autonomous differential equations are just zeros of the right hand side. Geometrically, the graph of any equilibrium solution is a horizontal line. Then, since the equation is autonomous, it means that if we have any single horizontal arrow, then all the arrows on the same level are also going to be horizontal. Because since the equation is autonomous, it means that remember that in every row of arrows, they have all the equal arrows. So then it means that we would have an equilibrium solution. Okay, then an equilibrium solution is called asymptotically stable if all other solutions approach that number, well, within a certain neighborhood of the number. Or an equilibrium solution is unstable if all other solutions they drift away from the equilibrium solution. So that's roughly how it works. Of course, it is probably not a very rigorous mathematical definition, but I suggest that you come up with a rigorous epsilon delta definition yourselves. It is possible to do, and I encourage you to think about it. Okay, so let us look at the examples. So here, this is the equilibrium solution, and all other solutions, they tend to drift away from the equilibrium solution, right? So here we have an unstable. Here, this is the exponential decay, so the right-hand side of the differential equation has a negative coefficient, so all solutions tend towards the equilibrium. So here we say that it is asymptotically stable. Asymptotically stable. So notice this word asymptotically that I didn't use here. They actually, as we will see later in the course, stable and asymptotically stable represent slightly different things, but for the difference will only matter for systems of differential equations. For a single differential equation, stable and asymptotically stable equilibrium are the same thing. So here is a logistic equation, alright, and for the logistic equation we have two equilibrium solutions, so one of them is 0, and 0 is unstable because above it arrows point upward and below it arrows point downward, so all the solutions tend to drift away. And the carrying capacity, K, so in this case it is 110. For it, right above it arrows look down, right below it arrows look up, so on both sides arrows look towards it, so which means that all the solutions are going to converge towards it, and hence the equilibrium is stable.